The instrument moving inside this animal's abdomen is being held by a general-purpose humanoid robot, not a surgical robot, the kind of walking machine you have seen in demo videos, costing roughly what a car costs, gripping a laparoscopic tool any hospital already keeps in a drawer. A senior surgeon drove every motion of it from a console, and on a standard surgical training drill, experienced surgeons made fewer errors driving this robot than they did holding the instruments in their own hands.
Laparoscopic means keyhole. The operation happens through a few small tubes pushed through the abdominal wall. What this team did through those tubes was take out a gallbladder. Twice, in 2 anesthetized pigs in a surgical simulation center. Both times the instruments cleared the tissue around the neck of the gallbladder until the surgeon could see the 2 structures he meant to cut and nothing else. The Czech surgeons call the critical view of safety. Both times the gallbladder came off the liver bed, and neither case was handed back to conventional laparoscopy or opened up. Nothing about it was autonomous. A human hand was on the controls for every millimeter. And the honest scoreboard is the author's own. The precision everyone assumed would fail is largely there. The speed, the reach, the sterile plumbing, and the calibration are not.
The paper comes from Zekai Liang and Michael Yip's robotics lab at UC San Diego's Engineering School, working with the university's own Department of Surgery. It was published in Nature in July 2026.
Here is what makes this an engineering result rather than a stunt. A laparoscopic instrument is not free to move. It goes in through a trocar, and from then on the shaft can slide in and out and spin, but it cannot shift sideways where it crosses the abdominal wall. It has to pivot about that one point. The name for it is the remote center of motion. Violate it, and the tool stops pivoting through the body wall and starts pushing against it. A davinci solves this in metal. Its arms are a linkage that is physically incapable of moving the shaft off the pivot. The geometry is set when the arm is docked to the port, and after that, the constraint is not something software gets to decide. A humanoid has nothing like that. Its arm is a shoulder, an elbow, and a wrist, exactly like yours, and none of those joints know where the trocar is. So the team put the constraint in software. Before the operation, they taped calibration boards to the trocars, flat black and white square markers that computer vision can read a position and angle from. The robot looks at them with the camera in its own head and works out where each pivot point is. From then on, the console does not command the arm at all. It commands the tip of the instrument. A solver works backwards through the whole chain, tip, shaft, mount, wrist, elbow, shoulder, for the one-arm pose that puts the tip where the surgeon asked while keeping the shaft crossing that pivot. It solves that in about 11 milliseconds and does it again every cycle for as long as the operation lasts.
That substitution has a price, and the bench measurements show where it lands. Asked to draw a straight line about 94 millimeters long, the instrument tip stayed within 1.3 millimeters of it. Asked for a circle 80 millimeters across, the error jumped to 10.4 millimeters. The circle stayed almost perfectly flat, off its plane by only 1.2, so the failure was not wobble, it was radius.
The reason is leverage. The wrist is outside the body. The tip is inside, and the pivot sits between them, so the shaft is a long lever. Tilt the estimate of that pivot by a fraction of a degree, and the error at the far end is much larger. The instruments made that worse in a mundane way. The manufacturer does not publish their internal dimensions, so the team measured the shaft lengths and joint offsets by hand and fed those numbers to the solver. A straight line forgives an error like that. A curve does not, because the direction the error points in keeps rotating as the tip goes round.
There is a second cost. From the surgeon's hand moving to the instrument moving took about 156 milliseconds. The target the paper cites for a surgical robot is under 150. Not disabling, but on the wrong side of the line, and the surgeon said they could feel it. Then they took it into a living animal, and the pivot stopped holding still. A pig breathes. The abdominal wall rises and falls, so the trocar rises and falls with it, and the robot's base drifts a little over an hour. The point the solver is defending is moving. If the estimate jumped from one camera frame to the next, the arm would lurch, so the team smoothed the estimated pivot over time. When it drifted too far, or the view got worse, or the surgeon did not like how the instrument was behaving, they stopped and recalibrated. That produced the least glamorous number in the paper, and one of the most telling. In the first case, they repositioned and recalibrated the robot 8 separate times, and active console time came to 56 minutes. In the second case, 4 redeployments and 32 minutes. Same surgeon, same procedure, 1 case of practice in between. Which brings back the claim from the start. 18 people, 12 with no medical training and 6 surgeons, ran a standard drill. Lift a rubber ring off a peg with one instrument, hand it across to the other, set it down on the far peg. Every mistake was scored and weighted by how bad it was. The 6 surgeons averaged a weighted error of 2.6 on the Humanoid. On a research version of the davinci, 3.8. With their own hands, 5.3. The gap over their own hands holds up statistically. The gap over the davinci does not, and the paper says so. On the harder certification task, the pattern held and then broke. Instrument collisions fell from about 8 per run by hand to 2 on the robot, and the certification score rose from 70 to 85. Then they put a clinical davinci XI on the same board. It finished in about 118 seconds. The Humanoid took 560, and the davinci scored close to 100. Precision is not this robot's problem. Almost everything around precision is. The everyday obstacles are worse than any of those numbers. Nothing on a commercial humanoid can go in an autoclave, so sterility was handled by pulling surgical gloves over the robot's arms. Workable in an animal lab, nowhere near acceptable in a human operating room. No clip applier fitted the robot, so when it came time to close off the duct, a surgeon clipped it by hand. They pulled one arm out of the field without undocking and then went back to the robot. The arms span about 45 centimeters, against roughly 1.5 meters to 1.80 meters for an adult, which is the real reason it kept having to be moved. And the surgeons reported it intermittently overheating. So why push through all that? Because of what sits on the other side. A modern davinci costs between about $1.5 and $2.5 million. Service runs around $175,000 a year. Its instruments are proprietary at hundreds to thousands of dollars a case, and the room usually gets rebuilt around it. The cart alone weighs the better part of a ton. That is why robotic surgery has stayed in well-funded hospitals. The machine in this study weighs about 27 kilograms and stands about 5 feet tall. Off the shelf, it costs roughly $20,000. The research configuration the lab used, with custom mounts, is in the tens of thousands. Part of that gap is just that a humanoid carries none of the regulatory weight a medical device does, and the paper says so. But the rest is real. It walks into an existing operating room and stands at an ordinary table, and its instruments are the wristed tools a hospital already buys. And because it is a general-purpose body, the same robot could hold a camera or retract tissue instead of operating. During one stretch of the first case, a second humanoid did exactly that. What this does not show is worth stating plainly. Nobody operated from another city. The console was in the room, and long-distance surgery was not tested here. Nothing in this system is cleared for a human patient. And the phrase the surgeons themselves used after driving it through 2 real operations was a distinct gap between technical feasibility and clinical readiness.
The useful thing about that sentence is which half is already finished. The hard part, the part everyone expected to be the wall, putting a millimeter-scale pivot inside a body that will not stop moving, using a machine with no pivot joint anywhere in it, worked. What is left is reach, speed, heat, and an arm you can actually sterilize. None of those need a new idea. They need better hardware.